So my name's Tim Melbourne. I have not been a long member of this community at all. I took over this geohazards focus area chair only this summer, so I'm sort of new into it. And I wanted to talk about giving you an example of why I took this on. And the principal thing that I'm going to be trying to do with this position over the next 2 years is and we've got a series of activities in place, but to basically open up to advocate for opening up global GNSS data sets for hazards and disaster risk mitigation. And I'm going to show you just a project that I've been involved with for over a year. So before I started doing this, about trying to build out a system in Oceania to enhance, not replace, not substitute, but just simply enhance, provide a fourth observation platform for an existing intergovernmental coordination for tsunami early warning systems. Okay, so that's the photo there is just a station that we built a few months ago. So a little bit about the outline of this talk, a little bit about Oceania, so you know what we're talking about if you're not familiar with it, is how tsunami warning systems work today in the globe. Okay, because tsunami is a big earthquake in Chile. A 9.5, say, what we had in 1960, will kill people around the Pacific Rim. So from the get-go, tsunami warning systems have been intergovernmental. There's a lot of data sharing, and that's coordinated currently through UNESCO and through the UN. So there are platforms for how that works. We run an analysis center, a global analysis center for real-time PPP that we provide for earthquake early warning. And if we can make this work for earthquake early warning, we can surely make it work for tsunami early warning, because earthquake early warning is a system where you characterize very quickly an earthquake has started. So say, and I'm going to show you an example from California, and then you notify everybody around before the surface waves arrive there. So that's measured in tenths of seconds, whereas tsunami early warning is measured in minutes. So, and then I'll show you a little bit about what we've been doing down in Oceania and then what the future will hold. Okay, so Oceania, it's a big region. It's almost 10 million square kilometers. It comprises 17, at least depending on how you count, 17 different nations or protectorates. So, for instance, the United States, Marshall Islands up here. Does this have a laser thing? How am I doing this wrong? There we go, got it. So the United States, the Marshall Islands up there is a protectorate of the United States. There's 14 actual countries in there. France is in there with French Polynesia. Chile's in there. The big dogs are kind of Australia and New Zealand. But there's just not that many stations in there. And I think so that's kind of the political, socio-political aspect of Oceania. I think it's much more interesting to look at the tectonic aspects of Oceania, because it's got some of the world's biggest undersea subduction zones that are absolutely shocking. And from a seismology standpoint, the Tonga Kermadec, which starts at the north end of the southern island of New Zealand and goes over 3,000 kilometers up to Samoa, it's almost uninstrumented. So, for instance, between off of New Zealand, the Hikurangi subduction zone, which is the southern end of the Tonga Kermadec subduction zone, between that and Raoul Island, which is right in the middle, you can fit two slip distributions from the 1960 Chile magnitude 9.5 earthquake. And if you never took a seismology class, the moment magnitude scale is log base 30 in energy. So that 1960 Chilean earthquake released more energy than all other earthquakes of the 20th century combined. Okay, so the thing is, when tsunamis get big, they can get really big. And there's not a lot of real estate in this part of the world where one could actually stick GNSS, but with the atmospheric, like the TEC elements, where you can actually see within minutes, the perturbation of the ionosphere with the penetrating GNSS signals, you can actually, just putting one station in the ground in Raoul opens up a huge sphere of potential tsunami monitoring. Okay, so there's a lot of very, very large subduction zones, and there's less than 24 GNSS stations running throughout Oceania. Zooming in on Tonga here, Tonga itself comprises over 1,000 islands grouped in roughly 5 large archipelagos. So we've kind of signaled in right here where we've been building out these stations. That's the trench there. You get very quickly, you just go 40 kilometers west of the big island of Tonga. and you are immediately in 10,000 meters of water. Okay, so it's, oh, and I should add the convergence rate between, this is the Lao Basin, which is spreading. So if you put a station in Chile and a station over here, the convergence rate between them is over 20 centimeters a year. And so things are really moving fast. And I mean, you can put a GNSS station in the ground and get a meaningful change in 2 weeks today. So it's really an amazingly fast place to move. So I'm from Central Washington University, which is in the state of Washington, which is on top of the United States, the continental US, the only subduction zone in the United States. And we have a history of 10,000 years that we've gotten back for all the tsunamis from the subduction zone ruptures. And when we go out looking for tsunami deposits, we look for sands and, you know, all the normal tsunami stuff. When you get down to Tonga, you get this is a tsunami deposit on the west side of the main island of Nuku'alofa. That's Darcy Snowden for scale. She's a physics professor at CWU. And you see, that's the biggest one. They call it Tsunami Rock. It's got a little plaque there, and it's been diagnosed. It was a recent tsunami only about 2,000 years ago that plucked that out of the reef. It's a volcano tsunami, but there are things like this all over the island. And when you talk to the modelers in the US and in France, has a big group working on this in Fiji, it's very easy to if you let this rupture go, like you just take some very conservative seismic estimates, put 50 meters of slip on a standard sort of subduction zone coupling that we know from Japan and places around the world. Don't do anything special and just let it rip. Okay, you will generate a tsunami that runs from one side of the main island of Nuku'alofa all the way to the other. Okay, 400,000 people swept into the ocean. And that could happen any day. So GNSS isn't going to save a lot of lives, but it's going to save some. And anything we can kind of do to help that situation is a good thing to do. So I'm not trying to scare people here, but that's it. You do not have to do special stuff in tsunami inundation modeling to really see a terrible outcome. That's why we're working down there. Okay, so, and I should add, when my first trip down there about 18 months ago, I thought, okay, I'm going to the main island of Tongatapu. I'm going to book a hotel. I went to book a hotel, put some stuff in there, but the calendar was screwed up. And this was the resort that I was actually trying to book a hotel at, which is missing. The website is still up today, but the resort is missing. This is so just over the horizon here is the Hunga Tonga eruption. So prior to January 2022, there were about 20 of these thriving kind of, you know, beachy, surfy resort places that were all wiped out in just the Hunga Tonga eruption. And as I mentioned, no matter where you go on these islands, you find tsunami deposits, not as big as that Tsunami Rock, but there's dozens of tsunami deposits that are, you know, 3 meters high, boulders plucked out of reefs. Okay, so that's Oceania. All right, so how can GNSS help this? Well, to answer that, you kind of have to ask the question, well, how does it work today? And so this is, I just lifted this off of the NOAA website. So in the United States, there's a federal law, it's called the Stafford Act, that says basically the USGS owns earthquakes and NOAA owns weather, including tsunamis. So this, under federal law, in our government, NOAA handles all of the tsunami warning systems. And so there's 3 bases of instruments that they currently use. There's the Global Seismic Network, which for the US is funded jointly by the USGS and the US National Science Foundation. And then there is data sharing between all the other nations, like France, like Germany, like China, that also run seismic networks around the globe. Okay, so that's one. And if you work in an operational center for tsunami warnings, for instance, in Honolulu, Hawaii, there's the US Pacific Tsunami Warning Center. They have a saying, if you're a duty scientist standing watch, you warn on seismic and you cancel on tide gauge. Okay. So essentially, because there's a lot of earthquakes that don't produce tsunamis, but it's the earthquakes that give that first notification, and you use the seismic network to find that. And then the next, so there's several hundred global seismic network seismometers that are reporting in. And then there's tide gauges, which are shared, again, around the globe. There's about 1,200 that they bring in. And then there's a very special kind of buoy called a dart buoy, which is essentially just an ocean bottom pressure sensor that's telemetered in real time through satellites. And so this detects the open ocean wave, which is very important. But Congress, United States Congress, only funds 39 of these. That's it, only 39 for the United States, for the globe. So spatially, this is quite limited in coverage. So this is how it works. You have the global seismic network, but there takes a time for the P and the S waves to propagate out, and you don't wait for surface waves to characterize the earthquake. You use something called the W phase, the whispering gallery mode, but it takes about 15 minutes depends a little bit on the geometry, but you're looking for roughly a 15-minute delay there. In a place like Tonga or the state of Washington, 15 minutes is longer than it's going to take the local tsunami to hit the shore. So what that forces is it forces the operational duty scientists they have to issue alerts immediately. Okay. You have dart buoys out there, but there's not very many of them, and you have the global tide gauge network. And I should add, the duty scientists will tell you this is a detection of last resort. You do not, if you you're inside a tsunami warning center, you do not want the wave to have hit a tide gauge before you understand what you're dealing with. Like, that's failure as far as they're concerned. It happens a lot. It's a tough world out there. But so GNSS offers a new kind of platform in which you can observe things in real time, and it's global in scope. And this is the thing, it is truly global in scope. And this is something the United States seismology community really struggles to understand, is how explosive GNSS has proliferated itself in the last 15, 20 years. And we're seeing it in many different ways, but like in the US, a lot of the seismic companies have been bought up by GPS or GNSS companies because they're much bigger and they're trying to merge types of observations. So this is a little bit like Benedict just showed. This is somewhat dated. This is 5 years old now, but this is everything that we pulled out of the UNR, University of Nevada, Reno Geodetic Lab site. And that's more like 25,000 stations today. I just haven't updated the figure. And then this is also about 3 years old. This is, we generated this figure by scraping public-facing casters to see what stations are available. So these are data that we've actually gotten and positioned in real time, okay? And the biggest thing that I'm gonna try to do in this new capacity as chair of the GGOS Geohazards Focus Area is to advocate through UNESCO, through the various intergovernmental coordinating groups, to get much more of these data, probably 80% of which are real-time telemetered in some capacity, to be shared for hazards warning, just like the seismic data is and the tide gauge data is to this day, okay? But generally speaking, is not. Let me add, okay, so where am I here on this topic? Okay, so I should add, and we know how to do this. We can add GNSS point positions, and there's lots of things you can do with GNSS. My little group of 5 of us at my university are focused entirely on point positioning and solid earth applications for disaster risk reduction. But, and we've been building this system for a dozen years, but it only last summer went live inside the US earthquake early warning system. Okay, so what my university does, our software, it's a real-time point positioning software. These are the big arrays, GNSS arrays. So we pull in the stations. There's about 1,050 stations. And we essentially position everything, and we hand off the positions to 3 universities. One is the University of Washington in Seattle, one is UC Berkeley here in California, and one is Caltech in Southern California. And that's where the decision modules are based. And those decision modules are bringing in all the seismic data, they're bringing in the GNSS data, they're triggering on earthquakes, and if in their algorithms, they see something that essentially triggers them, then they have to decide how big an area to warn, okay? And that warning area is now determined by GNSS inside Shake Alert. And it's live. I mean, it's kind of shocking to me personally, because there's only, like I said, 5 of us at my little university, and we do not want to be responsible for 25 million Californians getting an alert that they should not have gotten, but seems to work pretty well. The basis of the algorithm, just so you know, it is It's called PGD. It's a very blunt tool saying when earthquakes get big, they get really big, right? So this is just distance between a GNSS station and the hypocentral location of an earthquake. And so if you're 100 kilometers away and you move 10 centimeters, this is centimeters in log scale here, then you're looking at roughly a 7. And if you're 1,000 kilometers away and you move 10, or if you're 1,000 kilometers away and you move a meter, you're looking at a 9. So you can regress this very quickly, and that's the basis of the speed, okay? And so let me just give you an example. The system works, the GNSS system works. This is a fairly small earthquake in the scheme of things. It's a magnitude 7.2. In Ridgecrest, California, so it's sort of basically it's in that square here. So that's LA right there, and the Bay Area is right here. Our system, well, if you take what we call truth, which is take 2 days of measurements, so before the earthquake, wait 2 days, during which time there were tens of thousands of aftershocks, and look at the offsets, you get these blue vectors. This is what our system determined within 25 seconds, or these kind of greenish yellow victims. So they don't agree precisely, but they're pretty close. And there's actually, like I said, there's like 10,000 aftershocks between when our Kalman filters reconverged following the earthquake and what you found. And so over here, this is the actual times, the point position time series as they were seen in real time. There's no post-processing in this. If you're wondering how good they are, this is a comparison of the colored time series are what was available in real time. So we're talking by real time, a total latency of less than a second. And then it's compared with post-processing with GPX using, final products. And it's not exactly the same, but it's pretty good. And the point is for earthquake monitoring and characterization, it's good enough. And then if you want to know what truth is, this is a comparison between the black is the GNSS as available in real time, and then the blue this is pure seismology now, but you can take the teleseismic surface waves. You're not back projecting, you're solving an inversion to figure out if you have a fault. Imagine the fault has like a checkerboard pattern on it, and each sub-fault has a slip amount and a time. And so you figure that out, and this is done routinely by the USGS. It's called the finite fault slope rupture. And then you take that and you convolve that with, elastic Green's functions for the standard model used in locating earthquakes. And this is in absolute time. This is what you get. So the blue is essentially modern global seismology, and the black is GNSS. Okay, and they fit pretty well. And the key thing, or something like Shake Alert, was this is what we found. Our filters converged on the coseismic offsets within 25 seconds. And so this is where the strong ground motion was. And actually, Brendan Crowell at University of Washington, he has an AGU paper that showed he basically had figured out it was a magnitude 6.9 within 14 seconds. Okay. And so these rings show where the strong ground motion moving that propagates outwards at the speed of surface wave, which is typically about 3.5 kilometers per second. That's where the strong ground motion was when the GNSS actually converged on a solution. And interestingly, I was actually in LA for this earthquake. So I felt the ground shake, and I had running on my phone, My Shake LA, or whatever LA County has an app. Berkeley had another called My Shake, and then I also had the USGS one, and none of them went. It failed. It was a failure for Shake Alert. And the reason is because the seismic networks bogged down in data telemetry systems. And so we titled the paper, we titled it. So it's one of these papers where it's a BSSA paper. You only have to read the title. The title of the paper was 25-second determination of coseismic offsets from GNSS for this earthquake. And lo and behold, a year later, GNSS went live inside Shake Alert. Okay, so then we have a standard positioning system. I'm going to run out of time here, but basically we bring in all the corrections you need. So there's lots of stations, they go to casters. We bring in all the corrections, we position everything, and then we send it out the door. And it's all written from scratch to be very fast. And this is what you kind of want to see here. For all three of these, this top axis is seconds, okay? And so this is data telemetry. How long does it take to get data from and generally data, most of our signals come in within a second. And this is not distance here. This is router hops. Okay, so we We position New Zealand's data in Washington State, so we get data from their 100-station network. We position it and send the solutions back to New Zealand, and the round-trip travel time is under a second. So it's essentially instantaneous. And over here is completeness. So and within about a second and a half, you're up at 98% completeness for a billion, almost a billion solutions for 1 week. And these are the northeastern positions. So these are centimeters here. So we're generally doing within 4 to 5 centimeters. It's not sub-millimeter, but for earthquake monitoring, you don't need it. And for tsunami monitoring, you don't need it. And you can go to this website here if you want to see all this stuff. If you just go to panga.org, real-time GPS cockpit, you'll see all these vectors dancing around. This is one of a dozen or so, either web clients and then you can hook into it if you're a seismic network. And I should say the connection, I forgot to mention, the connection to tsunamis is that over the last 100 years, over 85% of big tsunamis have been triggered by earthquakes. So this is the Tonga pilot project. We basically have 100 receivers that we can deploy. I'm just going to show you some pictures of building them. We don't have a ton of dough. So what happened is we show up in Tonga. We ran a class. That's one of our field engineers. That's Darcy Snowden. She's the physics professor who's getting involved in this. So teaching the Tongans what they do. This is our monument. It's a 6-story concrete building. That's Vili Falau for scale. We show up, there's no such thing as, in America, we have OSHA, which is occupational safety stuff. There's none of that. You just put a ladder up, go in, drill a hole, dangle out over, 25 meters of empty space, no harnesses, no nothing. Bolt it in place, hook it up. Here it is. That's the first one. We go home. Oh yeah, I think they were regretting letting the Americans come through. We did not do this to their ceiling. Their ceiling was already busted through. But when we saw the hole, we were like, we can do this. So we got it going, get the data flowing, run a class, and then we go home. They have some firewall issues to it, and then we need a few days of data to get a good a priori position, and voila, there it is. Here's the time series. And this data is now going into JPL Guardian. It's going into the Pacific Tsunami Warning Systems in the US. So that was TNG1 down here in Tongatapu. TNG2 went up here in Nihao. There's another one. This is TNG3 on the islands of Hapai. I should add these monuments. Here's TNG4 went into. We have a test for these monuments. That guy, the Tongan guy, he weighs over 100 kilograms. So if he can do a pull-up off the monument, we say it's good enough. We don't have 10,000 euros to go build a proper monument. If we did, we would, we don't, right? So we're trying to, in American English, we would say, we're trying to build this with chewing gum and duct tape, right? So that's just to prove that we can do it. We thought if we can do it in Tonga, we can do it throughout Oceania. We have a working group here to try to get it going. It's slow going. We were supposed to have a conference in November. I delayed it for a year because the organization wasn't moving as quickly as we needed to, but there will be thing. And then I think my last slide here is, these are the various groups that are involved in this working group to try to put this Oceania together. And I wanted to end with this slide right here. This is one of the pieces of this that I'm interested in is capacity development. In our time in Tonga, by far the most aggressive and the go-getter of this group is this woman, Ansela Paea, and she's trained in geomatics at University in New Zealand. But if we're going to make this work and it's going to last, we need to train people like her. And so she really wants to come to the US, come to my university, but we have to come up with essentially $40,000 US a year to support her between tuition and living expenses. And so, you know, money at some level is the mother's milk of science. Part of this is to try to get the funding together, not just to build out this network, but to bring the people in so that when they go back, they run it at a standard that we're expected to. Because if we show up, build a network, and then walk away, the network will be dead within a year or two. So we're deeply aware of that. And I think that is my last picture. All right, thank you.
Tim, are there questions or comments? The online colleagues? No?
Yeah.
Okay.
Hi, thank you for that excellent presentation. You showed at the beginning two pictures of the GNSS receivers. One of them, the top one with many of them, I don't remember what you said it was. So that was one question. And the other one, you said that you scrapped them from casters, and how does that work? And is there much overlap, or did you discover new ones that were not available in your first?
Yeah, so where are these receivers coming from? So this is a strange story, but you might remember the Great Recession in the United States kind of took out the global economy. The federal government in the United States printed $1 trillion and said, spend it. And so the Department of Interior got a bunch of money and they bought 100 TopCon receivers. They're net G3As with choke ring antennas, but they do not have Galileo. They're GPS and GLONASS, and all of our partners want Galileo. So what happened was 100 perfectly good receivers got pulled out. 60 came from our network, 40 from Berkeley's and Caltech's, and they were literally going to get thrown away. They were going to go to a landfill. And so my son and I, just because you don't let $2 million worth of receivers be thrown away, we got in a truck and we drove down 3 years ago and grabbed them. So that's where these receivers are coming from. They're perfectly good TopCon Japanese receivers. I mean, if they were a car, they are not a 2025 Tesla. They are a 2013 Toyota Camry. But if you just need a car with 50,000 kilometers on it, if you just need a car, they're perfectly good. I have a student testing them. He's tested about 70 of them, and he's found 4 failures in 70. So they're perfectly good. So that's the first question. So we're deploying those. They're free. The second question was, how do we scrape a caster? Yeah, so caster, caster has some address and it's got a source table, which is always 20:2101, I think it is. So we just wrote a web client, and I got a list of known casters, and the web client just loops through each one, hits it, scans it, pulls in all the stations that are listed, and repeats once a week and looks for new stations on 100 or so casters. That's how it's like an FTP scrape. It's just scraping. And this is a thing.
Yes, the coffee break will be shorter.
Sorry, so you mentioned working with Guardian,
yeah.
Right? From my memory, I work at GGOS, and we just took Guardian on and started hosting their near real time. I remember them only having about 80 stations they're working with, and your density on California alone looked amazing to me. So what are the pros and cons that you see with working with them? And do you have a good relationship where you know each other's strengths and weaknesses? And yeah.
Yeah, so as soon as we got TNG1 streaming in, and as soon as we get the other one streaming in, that's contingent on Tongan, the usual firewall stuff, we called Guardian at JPL and said, do you want to use this data? And because we need to see this data used if these stations are going to get supported. So that's answering your second question. It's either synergistic or mutually parasitic. I don't know how you would characterize it, but it was very important for us to get these data into the tsunami warning systems and into Guardian type TEC stuff. Okay, so that's the first question. Second question, how do we generally work with them? Great. I mean, that's a great group at JPL. Third is, all right, for California, I mean, they're doing TEC stuff. You don't need that station density that California has, or the West Coast. You just don't need it. So from a TEC physics standpoint, I think a station every 100 kilometers is probably enough.
Yeah,
so,
perfect.
Yeah.
Thank you.